So there's a little bit of stuff to remember for finding your eigenvalues. One of the things that we need to do, I'm going to go ahead and change these to A's just so my notation is consistent and I don't confuse anyone. So this one, we're going to be looking for the determinant of A minus lambda times the identity matrix. And then that determinant is going to be really useful for us. So this lambda times identity matrix, I think, is something that people struggle with when they're first understanding what's going on here. So remember that lambda is just a scalar in this case, right? And then our identity matrix, we have a 3 by 3 going on, so we're going to want a 3 by 3 identity. That's just the matrix that has the diagonal of 1s and everything else is 0. So that's the identity matrix. From there, a scalar multiplication of a matrix, you apply that scalar to every term in the matrix. So in this case, all these zeros stay zeros, and then all your 1s become lambdas, right? So now we have a matrix that has lambdas as our diagonal and zeros everywhere else. Now where that's useful is we're going to go ahead and subtract that from this A. So now we have this A minus lambda in all our diagonals and a bunch of zeros. Since this is matrix addition and subtraction, there's nothing really too fancy here. You're just going to go spot to spot across and make sure you match them up and just do the subtraction. Now technically you would want to do addition here and turn all of these negative, so I'll go ahead and do that here. Because we don't really subtract or divide matrices, we have other operations that we use. In this case we would actually have multiplied by a negative lambda to get all of these to be negative. And that distinction is important for very specific applications, but overall, as long as you know that we're about to add these together, we'll be okay. So this matrix here is going to give us 1 minus lambda, and then 3 and 2 are going to stay the same because they are multiplied, or they're added with just a 0. So you have 3 and you have 2, and then this 1 is going to stay the same. Now 0 minus lambda is still important because it's addition and subtraction, so it doesn't just go away. So in this case, it's just negative lambda. And then we have our 4 is going to stay the same. Then we have 2 and 1 are staying the same here because there's zeros here, and then 2 minus lambda. So now what we're going to do is we're going to take the determinant of this matrix. And so the determinant here, we're going to do it kind of like we did earlier, but the thing to remember, cool. So we got the matrix of 2, 3, 1, and 4. And since we've already done the hard part, we'll do this one since it's nice and straightforward, and I have a correct answer that I can check it against. Great, so we're still going to do this minus lambda times the identity, so our diagonals are going to become subtracted by lambda. So we're going to get the determinant of A, where A is now going to be, so this is A minus lambda I, 2 minus lambda, 4 minus lambda, and then you have your 3 and your 1 stay the same. And then we're going to do our quick little determinant. So in this case, our determinant of this right here is going to be 2 minus lambda times 4 minus lambda, and then minus 3 times 1, which is just 3. We can FOIL this out real quick. So we have 8 minus 4 lambda minus 2 lambda minus 3. Simplify this out, we get negative 6 lambda plus 5. Is that right? Yep, looks good. And then that's our determinant piece. Now recall, we're going to choose values for lambda that make this determinant equal to 0. So in this case, this is a linear equation. So this is, oh, I did something wrong. Whoopsies. Yeah, it shouldn't be linear. Negative lambda is going to be lambda squared. Important. Okay. I'm going to rewrite this real quick in standard form just so we can really clearly see how we're going to factor this. Nice and easy. So negative in the middle, positive on the end. That tells me that both of my factors are negative in the middle since my original is positive. And then 6 coming out of 5, so I know that it has to be 5 and 1. And if we check this out real quick, it should work out. So lambda times lambda squared, negative 5 times negative 1 is positive 5, and then 5 lambda and 1 lambda, negative 6. So that worked out really nicely. And so that equals 0. So now our roots, just going back to algebra 1, are just the numbers that make any of these individually 0. So we can plug in a 5 here and a 1 here, both of those make it 0. This is where you have some choices to make, And these choices don't matter, but you have to keep them the same through the rest of the problem. You have to decide which one of these is your first and second eigenvalue. And it doesn't matter which one you choose, but you have to be consistent for the rest of the problem or the whole thing messes up. So let's just call this one eigenvalue 1 and that one eigenvalue 2, just so we can keep our lives simple. So we're going to write up here, we have lambda 1 is equal to 1, and lambda 2 is equal to 5, right? So from there, the process is pretty straightforward, but it can be a little confusing at the very last piece. So I'm going to go a little bit quickly through this just to make sure that we can get there pretty reasonably fast. And then we'll just kind of talk about where I see my students that I mentor and tutor mess up the most. So we'll go from there. So we're going to go back to this matrix here. We're not doing a determinant anymore. We're just going back to this matrix itself. So we have 2 minus lambda, 3, 1, and 4 minus lambda. We will end up doing a determinant, but for just the moment, we're going to look at this again. So we have lambda values, and we have this matrix that has lambdas in it. What we're going to do is we're going to plug in these lambda values individually, and then we're going to take this matrix and solve it using all of our determinant properties that we can use, including you can use your row operations and stuff like that as well. Because ideally, we should get a linearly dependent matrix because we're uncoupling these two lambda values from each other so we can get a scaling factor. And then once we do that, we'll be able to solve for our actual vector. So let's go ahead and do this determinant after we plug in our first value. So we're going to say lambda 1 is what we're plugging in first. And so we have 2 minus 1, 3, 1, 4 minus 1. And then now we can do our determinant after we do our algebra. So this becomes 1, and this becomes 3. I'm sorry, we're not doing a determinant. I was right to say that earlier, and I doubted myself. So what we do here is we can take these and use our row operations. So we have 1 and 3 and 1 and 3. So I think we can pretty clearly see that if we take a negative row 1 and add that to row 2, we're going to get a matrix where the first row exists and the second row doesn't. So now we have this free variable here in our second value. So our free variable, we're going to label these, instead of x1 and x2, we're going to go ahead and label these k1 and k2. And that's just convention, but you'll see why here in a second. So now if we write these into a traditional expression like we would normally do, we would have 1k1 plus, since this is positive, 3k2, right? And then the other piece of this is that this is still equal to 0. That's the point of why we're doing all this, is because we have a way to make this homogeneous, equal to 0. I don't know why I wrote 3. My brain doesn't work when I'm talking and writing, I guess. Okay, so pretty much what we're going to do is we're going to solve this out for just k1. We're going to parameterize k2, and then we'll finish out. So k1 is just k1. We'll subtract 3k2 to the other side. Now we can let k2 equal t. So this k2 now becomes, I'm going to rewrite it here, so k1 is equal to negative 3t. Now here's one of the other conventions that you have to do and make sure you're careful about. It does not matter what value t is. It matters that k2 and k1 are both integers. They don't have to be positive, but they have to be integers. So they have to be actual whole numbers. In this case, it's going to work out pretty nicely. We're just going to plug in 1 for t, and it'll work out pretty well for us. So if we plug in t equals 1, then this becomes k1 is equal to negative 3. So that one worked out pretty nice. So our vector k1 is equal to k1 here is negative 3, and k2 is 1. This vector is tied to this eigenvalue. Super, super important we don't mess that up, especially if you're going to take differential equations later. If you decouple this from this and you use this eigenvector with this eigenvalue, your whole solution is going to mess up. It'll be completely ugly and probably wrong. It would be very, very rare that it would work out correctly. So that's our eigenvector that goes with this eigenvalue. Clear out some space, and actually I'll just rewrite that one here. Hopefully that's not confusing. I'll write the other one right next to it. And we're going to solve for that one right now. Cool. So let's back up to that piece. And hopefully you can get a little ahead of me on this one. So here, instead of lambda 1, now we're going to lambda 2 into that matrix. So we have 2 minus 5, 3, 1, and then 4 minus 5, right? So now we're going to use just normal algebra real quick to clean this up, simplify inside, and then we can try and use our row manipulations. So we have negative 3, and 3, and then 1, and negative 1. Well, now I can see this is negative, that's positive, so I can use 1/3 row 1 plus row 2, and that should kill this bottom row. So I multiply that by 1/3, I get negative 1 plus 1 is 0, and then 3 times 1/3 is 1, minus 1 is 0. So that gives me what I want. I get negative 3 and 3 over 0 and 0, and that's still equal to 0, right? And I'm going to reuse K1 and K2 because that is just okay for me and it's easier to keep track of than trying to use new variables. Just remember that they are separate, right? They're not the same variables, so it's totally okay. And in this case, we're still solving for K1. You see that they're both 3, so we can probably just eliminate the 3 by dividing everything by 3, which is what I'm going to do. And this one's negative, so I'm going to add this one to the other side. And all of that at once means that K1 is equal to K2. So in this case, when we let K2 equal T, in this particular one, T is just going to be 1 again, which is fine. It's not always like that, but in this one it worked out that way, so it's totally okay. So then when we go back and plug in our 1, we get a 1 here, and then K1 is equal to K2, which is equal to T, which is equal to 1, so K1 is equal to 1. So our vector, our eigenvector K2 is equal to 1 over 1. Okay? So one of them, and they're coupled together, these two go together. So one of them is your diagonalized matrix. So in this one, you're going to write your eigenvalues in your diagonal, which that should look really familiar because originally we had a diagonalized matrix that we subtracted from A. So now that's our diagonalized matrix. I don't remember why we call this other one P. It probably means something, but I don't think it's important for us to know what it means. But the way that this works is if this is lambda 1, this has to be eigenvector 1 in this column. And if this is lambda 2, this has to be eigenvector 2. They are so important that you keep them in the right order, or else none of this stuff actually works and you just get some erroneous answer, if you can even get an answer. Notice I wrote these as column vectors. I did that on purpose. They're column vectors here because I want them to be in a column here. So my eigenvector 1 goes with eigenvalue 1. Eigenvalue 1 is in our first column, so eigenvector 1 consists of our first column in our P matrix. And we'll do the same thing with eigenvector 2, and that's 1 and 1.